Good morning, everyone. So sorry for canceling the last class, and I wanted to give you the record for the last class, but I thought that maybe it will be a good idea to go over the chapter 8 together, because this chapter is really important for the next few chapters, because we'll be using the concept, similar concept to solve the problem in the later chapter. And I think we'll be able to finish the syllabus one time, and if we need more classes, in that case I will record some extra classes and I'll post on YouTube. Yeah, and I will send you the link, okay, if needed. Okay, so in the last class, we canceled, so class before the last class, I think we finished almost section 8.1 and section 8.2. And in today's class we'll try to complete the rest of the topics from chapter 8, and then we'll start chapter 9. Okay, do you have any question about whom? Oh, I have already posted your exam on grade on Blackboard. So if you have any question, you can about your grade, you can email me. Or if you find any inconsistency in grade, then you can email me and I'll try to look into it and I'll fix it. Okay. Yeah, the quiz. Yes, you will have quiz this week, and it's one Thursday. So one Thursday, I'll give you a quiz, and it will be the last 30 minutes of the class. And this quiz will cover chapter 7 and chapter 8. So you will have 4 to 5 questions in the quiz. Yeah, not 5 actually, you will have 4 questions in the quiz. So 2 questions from chapter 7 and 2 from chapter 8. Any other question? Okay, so if you do not have any other question, then we'll move to the lecture. Okay. So sample size for estimating mu. So to estimate mu, we use the sample mean, right? So to estimate mu, we use sample mean X bar. So this is called the point estimate. And to estimate mu, we also use confidence interval, right? Now, till now, we learned 2 types of estimation of the parameter mu. One is the point estimate, and the second one is the interval estimate. And the interval is, yes, the quiz will be on Thursday. That's correct. So we use point estimate, and we also use interval estimate. For interval estimate, we have 2 numbers. One is the lower limit of the interval, which is X bar minus E, and E is the margin of error. And we have also the upper limit of the interval. So this is interval estimate, and that is called confidence interval. So now the question is, when we increase the sample size. So for example, if in our class, there are total 134 students in our class. So you have already taken your exam on, and you know the exam on grade. So if we want, and the population is all the students in this class. So the population mean will be the average grade of exam on for all students. And sample mean is if we collect a sample, for example, maybe size 10 or 20, that's mean we'll only ask 20 or 10 students about their exam on score, and we'll calculate the average. And suppose we do not want to ask every student in the class about their score and find the parameter mu. We just want to ask few students, a couple of students. And we can make inference about the population mean based on the sample mean. So now, if we increase the sample size, what will happen? So we have 134 students, and the population mean mu is the average score for all the students, and X bar is the average score of the selected students. Now, if we first ask 10 students about their score and calculate the average, and based on this, if we make inference about the class average, that estimate might not be very good estimate. But if we increase the sample size, if we increase 20 students, then we might have better result. If we ask 30 students about their score and take the average, that will better estimate the mu. And if we ask 50 students, that will give us even better results. So that's mean if we increase the sample size, we'll have better estimate. Now the question is, so that's mean if we have large sample, then we'll have better estimate. Now the question is, how large is the large? That's mean what should be the appropriate n to estimate mu? So because in some study, it is really hard to collect data. So in that case, we do not want to collect excess data. That's mean we want to collect only the data which is required. We do not want to collect more data. So in that case, before collecting the data, you need to fix the sample size. So that's mean we need to fix n. And after that, we'll collect the data. So now how do we fix the sample size n? So what sample size is the appropriate sample size? To determine this, first we need to fix the error. That's mean how much margin of error we want to have, and what is the standard deviation of the data, and the critical value. That's mean z alpha over 2. So that's mean how much type of error we will consider, how much alpha we'll consider. Okay, then we can use this formula. N is equal z alpha over 2 times sigma divided by e whole squared. So you can use this formula to determine the sample size n. And if n is always sample size cannot be a fractional number, right? Cannot be a fraction. So that's why if you have a fraction for sample size n, you will always round up to the nearest whole number. And that will be the minimum sample size to have a better estimate of mu. Actually, this formula came, okay. So now we'll go over some example. So the first one is find the confidence level and alpha for an 82% confidence interval, and what is the confidence level? Determine the value of alpha. Okay, so before going to that problem, I want to show you how the sample size play a role in estimating mu, or in estimating or constructing the confidence interval for mu. So I'm sharing this applet. Okay. So here you can see, so our original distribution is right skewed, or it could be also normal distribution or any other distribution. So for example, it is right skewed, and the mean is 50, or you can also consider different mean, and the standard deviation is 10. Now we will see if we increase the sample size, then what will happen to the confidence interval. So let's first start with sample size 10. Then this is an applet. You can also see this one. This is very nice actually. So here our population mean is 50 and the standard deviation sigma is equals to 10. So now we'll construct confidence interval for sample size 10, and our confidence level is 90%, and we will construct, yeah, the sample size is 10. Okay. So this is the confidence interval. We have here 100 confidence interval. So we constructed 100 confidence interval with sample size 10. So now you can see that the confidence interval are very wide, and the green confidence and green lines, those confidence interval covered the original mean, the population mean 50, and the red intervals, they didn't cover the population mean. So that's mean there is some error, right? So this is called the, and it will determine by how much error we will tolerate. It will be determined by the value of alpha. So in that case, the alpha is 5%, because our confidence level here, this is 95%. So alpha is 1 minus 95, that's mean 5%. So that's mean here we will tolerate 5% error or 5% mistake. So that's mean we are 95% confidence. That's mean there is only 5% chance that our interval will, if we construct 100 intervals, then 5% interval will not cover the population mean. But 95%, we are confident that 95% of the 100 intervals will cover the confidence mean. Will cover the population mean. Yeah. So now increase the sample size. So if we increase the sample size, make it 20, then what will happen? Do you see any change in the confidence interval? Anyone? So what happened to the confidence intervals when we increase the sample size? Did you notice anything?
Didn't it stay the same?
Okay, so let's increase a little bit more. So make it 50. So this is for 20. So now we'll increase the sample size, make it 50, and you will see the results. Now the difference is obvious, right? So what is the difference you have noticed? Anyone? What did you observe here when we increase the sample size?
They get closer to the mean.
Is it become wider or narrower? What do you think? Yeah, they are narrower, right? So when we increase the sample size, the confidence intervals became narrower. Yeah, that's correct. Thank you. Yeah. So that's mean when we have large sample, the confidence interval will be more precise, right? They will be close to the actual value of mu. So that's mean we will have more precise interval when we'll have large sample. And we can increase more if you make it 100, if you make it, okay, so let's make it sample size 200 and let's see what happened. Yeah, it's even more narrower, right? So that's mean when we increase the sample size, we'll have more precise confidence interval. So that's why determining the sample size is really important before collecting data. So because if you consider very small sample size, then the confidence interval will not be a very good, it will not have a very good confidence interval. It will not be a very precise confidence interval. Yeah. Okay, so now we'll go over some example. Find the confidence level and alpha for an 82% confidence interval. And what is the confidence level? Determine the value of alpha. So we have to construct 82% confidence interval. So this 82% is called confidence level. So that's mean the confidence level is equal 82%. So this is 0.82. So now we have to determine the alpha, which is the level of significance. So the alpha is 1 minus the confidence level. So that's mean 1 minus 0.82. So this is then 0.18. So this alpha is also called type 1 error. So we'll learn this thing in the next chapter. So alpha is the level of significance. Alpha is called level of significance. So that will determine how much type 1 error we will tolerate to do a hypothesis test or to construct a confidence interval. So here alpha is the 1 minus confidence level. So we have more example for the provider sample mean, sample size. So we have the sample mean, we have sample size, and population standard deviation. So we have to complete pairs A through C. So here the sample mean X bar is 37. The sample size N is equal 100. And standard deviation, population standard deviation, sigma is 2. So now we have to find a 95% confidence interval for the population mean. So find the 95% confidence interval. So what is the confidence level here? So what is confidence level here? And what is the level of significance? Level of significance is alpha. Yeah, level of significance is 0.05. That's correct. And confidence level is 0.95. And level of significance is 1 minus 0.95. So it will be 0.05. And X bar is 37, N is 100. So first we need to find the confidence interval. So to find the confidence interval, so what type of confidence interval we'll construct in this case? Here sigma is 2, who is this population mean, this population standard deviation. This is known. So to construct confidence interval, we need some assumption. So for Z interval, we need assumption that the sample size, the population is either normal distribution or the sample size is large, and sigma is known. So what assumptions do we have here? Sigma is known. This is 2. So we know the value of sigma. That's one assumption. And the sample size N is 100. So is it a large sample size or a small sample size? What do you think? Is it large or a small? Yes, that's correct. This is large sample size, right? Because we consider the sample size large when it is greater than 30. So in this case, we can use Z interval, right? We can construct Z interval to construct the confidence interval. So what is the formula for the confidence interval? This is X bar plus minus Z alpha over 2 times sigma over a square root of N. So this is the formula to construct the confidence interval. Okay, so now we'll try to construct the confidence interval. So our formula is X bar plus minus Z alpha over 2 times sigma over a square root of N, where X bar is from the previous slide, X bar is 37, N equals to 100, and sigma is equal to, and alpha is 0.05. So we need Z alpha over 2. So that's mean we need to also calculate alpha over 2. So this is 0.025. So first we need to find Z alpha over 2. So what is the value of Z alpha over 2? And other informations we have, right? So we only need this information. We need to find this information. We have sigma, we have N, and we have also X bar. So we can plug in all this number. This is 37 plus minus we have sigma, which is 2, square root of 100. But we need to find z alpha over 2. So how can we find this one? Z alpha over 2 is the 0.025. That's mean it is normal distribution, and this area is 0.025. So that's mean the area on the left side is 0.975. Yes. So now we need to find the z score, corresponding z score, and you know how to find the corresponding z score. So we need the z table in this case. So let's look at the z table. Okay, so we have the z table here. So let me share the z table with you. Yeah, so this is the z table. So now we need to find the value of z score when alpha is 0.025, but we have to look at actually 0.975, or we can also look at 0.025. So if you look at 0.025, the area is 0.025. So this is 0.24. So this is 0.025. Sorry, no, this is not 0.0025, but we have to look at 0.025. I'm sorry, this is not the correct one. 0.022, 0.027, 0.028, 0.024. Yeah, this is 0.025. So there is 0.025. The value of z is 1.96. So here we have negative, but do you consider the negative value or the positive value? So let's go back to the slide. So now you can see the z score is on the right side, right? But since we look at 0.025, it's giving us negative value. But if you look at 0.975, it will give you positive value. But the values are same. The only difference is if you look at 0.975, you will get negative value. And if you look at 0.025, it will give you, sorry, it will give you, yeah, the negative. If you look at 0.025, it will give you negative value. If you look at 0.975, it will directly give you the positive value. But the value are same. The only difference is the sign. Now you have to determine which value you'll consider. So since z alpha over 2 is on the right side, so it is always positive. So that's why you have to consider the positive value of z score. So it will be 1.96. Now we have all the informations. We have x bar, we have z alpha over 2, we have sigma, we have n. So we need to simplify this one. So if you simplify this one, then it will be 37 plus minus 1.96 times 2 divide square root of 100. So that's 10. So this is 0.392. So then it will be, then we will have two numbers, 37 minus this one and 37 plus this one. So 37 minus 0.392, which is 36.608. And the second number will be 37 plus 0.392. So that will be 37.392. So this is the confidence interval. This is the 95% confidence interval. So do you have any question? So how did we get this number and this number? So we have two numbers, plus and minus. So 37 plus is this number, and 37 minus is this number. Because if you subtract the margin of, this is called the margin of error, which is E. This is margin of error. So if you subtract the margin of error from the point estimate, you will get the lower limit of the confidence interval. And if you add this number with the sample mean, you will get the upper limit of the confidence interval. So this is our confidence interval. So now how do we interpret this confidence interval? So we'll interpret this confidence interval this way. Okay, so identify and interpret the margin of error. So in A, we calculated the confidence interval, and the confidence interval was 37.392. So in part B, we need to identify and interpret the margin of error. So now we need to find the margin of error. So how do we calculate the margin of error E? So this is actually X bar plus minus E. So this part is the margin of error. And we calculated this on the confidence interval was 37 plus minus 0.392. So what is the margin of error? The margin of error is E is equal 0.392. So this is the margin of error. So that's mean the population mean, we are 95% confident that the population mean will be within 0.392 from 37, from the either side of 37. So that's mean the population mean mu will be within this value from the either side of 37. So that's the interpretation of the margin of error. So the next part is express the endpoints of the confidence interval in terms of the point estimate and the margin of error. So that's when we have to express this one as X bar. So we have already done it. So this, you have to express this one as 37 plus minus 0.392. So you're already done with this. Okay, so how did we find E? That good question. Thank you. So here X bar plus minus Z alpha over 2 times sigma over square root of n. This part is margin of error. This part will give you the value of E. So we already calculated this part, right? Because this part is, this is 1.19 on 1.96. So, and we calculated this one's 37 plus minus 0.392, right? So this part is then E. So which is the margin of error? Yeah, that's a very good question. So is that answer your question? Okay, thank you. So now we'll go over some more examples. A simple random sample of 20 automobile models yielded the data shown to the right on fuel tank capacity in gallons. So we have this data set. Now we have to find a point estimate of the mean fuel tank capacity for all new automobiles model. So we need to find the point estimate of the mean. So how do we find the point estimate of the mean? The point estimate of the mean is X bar. The mean is mu. So we want to estimate this one, and the point estimate is X bar. So that's mean we have to calculate X bar. So in part A, we are given the sigma of Xi is equal 369.8. So that's mean this is the sum of all the values. So now we need to calculate X bar, and we know that X bar is sigma of Xi divided by N, which is 369.8. And what is the sample size here? This is 20, this is 8, this is 0, 20. So it will be then 369.8 divided by 20. So it will be 18.49. So it will be 18.49. So this is the point estimate of the mean. So now determine a 95% interval for the mean fuel tank capacity of all new automobiles. So we have to, and where sigma is 3.40. So we have to construct a 95% confidence interval. Okay, so let's construct a 95% confidence interval. So what information do we have? We have here X bar. So let's write down all the information here. So we need X bar in part B. This is 18.49. And we also need alpha. So what is alpha here? Yes, we have 18.49. That's correct. So what is the value of alpha? So we'll construct 95% confidence interval. So what is the value of alpha? Yes, 0.05. That's correct. Thank you. This is, yeah, I think, yeah, this is 0.05. That's correct. So alpha is 0.05. Great. So we have alpha, which is 0.05. And we also need the standard deviation. Sigma is equals to 3.40. We need sigma, which is 3.40. Yeah, that's correct. 3.4. And the sample size is 20. And we also will construct the confidence interval plus minus z alpha over 2 times sigma over a square root of n. So we need to find this. Okay, so now the question is, what type of confidence interval we can use in this case? Can we use the z interval in this case? Yeah, we can, because we only learned z interval, right? I'm just kidding. So we will also learn some another type of confidence interval like t interval. So we'll only learn these two. So z interval and t interval. So for confidence interval, we know that if the sample size is large and sigma is known, we can use z interval. But here the sample size is 20, which we usually do not consider as large sample size, right? Okay, but for confidence interval, if the data set doesn't have any outliers or doesn't indicate that this is far away from the normal distribution, then if the sample size is 15 or more than 15, we can use the interval. So here, if you look at the data, I do not see any potential outliers, right? All the data are like very close. So we do not have, I don't think that the data has clear outliers. So that means there is no clear indication that this data is far away. Sorry, this data is skewed or far away from the normal distribution. And this is also field data. So it should be approximately normal distribution. Okay, so in that case, we can also use z interval. Since sigma is known and we have all the information, so we can use z interval. So now we need to find the value of z alpha over 2. So alpha is 0.05. So alpha over 2 will be 0.025. And what is the value of z 0.025? Anyone? You have to find it from z table. So what is the value of z 0.025? What is the z score? Okay, so if you remember it from the previous example, so we already found it, right? Z 0.025. So what did we find? What did we get for z 0.025 in the previous example? 1.96. That's correct. Thank you. So z 0.025 is 1.96. So we do not need to calculate it again, or we do not need to find it again from the z table because we already have this. Yeah, this is 1.96. That's correct. So now we have x bar, which is 8.49 plus minus, this is 1.96 times sigma over, sigma is 3.4 over a square root of n. So now if you simplify this one, you will get two numbers. So this will be then 18.49 plus minus 1.96 times 3.4 divide a square root of 20. Then you will get 1.4 1.49. This is 1.49, and this is the margin of error. So now we have the point estimate and we have margin of error. So if you subtract margin of error from the point estimate, you will get the lower limit of the confidence interval. And if you add the margin of error with the point estimate, you will get the upper limit of the confidence interval. So that's when we already have the confidence interval, and which is 95% confidence interval. Okay, so now I'll go over one more example. A sample mean, sample size, population standard deviation, and confidence level are provided. So we have the confidence level, we have point estimate or sample mean, we have the sample size and sigma. So here X bar is 51, N is 16, and sigma is 4. The level of confidence is 99%. So what is the value of alpha in this case? So that's mean alpha is 1.99, which is 0.01. So alpha is 1% here. So identify the critical value. So we need to calculate, we need to find Z alpha over 2. So that's mean we need to find Z 0.005. So we need to find this Z score. So let's find the Z score first. So let's go to the Z table and find the Z score. So our alpha is 0.005. That's mean the area is 0.005. So where is 0.005? Yeah, this is, no, not this one. 0.005 is 0.5, 0.6, 0.52, 0.51. So this is between these two numbers, right? Yeah. This is 0.0051. This is 0.0049. So that's mean it will be then 2.5 and average of 7.8. So 2.57 plus 2.58 divided by 2. So that's mean it will be then 2.575. So this is the Z score. So we are not considering negative. We have, though we have negative number here, but we are not considering negative number because for Z score, the Z is on the right side of the distribution. So it will be always positive. This is 2.575. Okay, so we have the Z score. Which is 2.575. So now we have to calculate the margin of error. So what is the margin of error? Margin of error is Z alpha over 2 times sigma over square root of N. So that's mean 2.575 times sigma is 4 over square root of N. N is 16. So it will be 2.575. Yeah, the answer is 2.575. So this is the margin of error. So we have one more example here. So a 95%, we are not going to solve this problem completely, but I'm just giving you the idea how to solve it. So 95% confidence interval of 16.6 months to 50 months has been found for the mean duration of imprisonment. So we have to estimate mu, determine the margin of error. So first we need to find the margin of error, which is Z alpha over 2 times sigma over square root of N. So what is the alpha here? Alpha is 0.05, and we have actually the confidence interval is given. So a confidence interval of 16.6 months to 50. So the confidence interval is 16.6 to 50. So this is the confidence interval. So the width of the confidence interval is 50 minus 16.6. So that will give us the width of the confidence interval. So 50 minus 16.6. So which is 33.4. And the margin of error, this is also a formula to find the margin of error. There is another formula if we know the width of the confidence interval divided by 2. So that's been 33.4 divided by 2. So which is 16.7. So this is the margin of error. So now you have to explain the margin of error in the context. So see, find the sample size required to have a margin of error of 12 months. So that's when we want to have a margin of error in part C. We want to have E is 12 months and a 99% confidence, then alpha is 0.01. Yeah, alpha is 0.01. You have to find the value of E. Sorry, you have to find the sample size N. So to find the sample size N, we already know the formula. N is equal Z alpha over 2 times sigma divided by E whole square. And that will give you the sample size. Okay, so do you have any question? If not, then we'll go to the next section. This is the last section from this chapter. And which is confidence interval for one population mean when sigma is unknown. So till now we discussed confidence interval where sigma is known. So that's mean the population standard deviation was a known value. We know the value of sigma. So now we'll discuss the confidence interval where sigma is unknown. So that's when we do not know the value of sigma. Okay, so what will happen if we do not know the value of sigma? So what is the difference between these two? When we know the value of sigma and when we do not know the value of sigma. Okay, so when we know the value of sigma, if x is our original variable, then the z-score is x minus mu divided by sigma over square root of n. When sigma is known. But when sigma is unknown, so we use the test statistic S, which is standard deviation to estimate sigma, right? So we use the sample standard deviation to estimate sigma. So in this case, the z-score is equal x bar minus mu divided by S over square root of n. Okay, so in this case, x is random variable and mu is a fixed value, right? Mu is the population mean, which is just a single number, and sigma is the population standard deviation, which is also a single number. So that's mean here the only variable is x. X is the random variable, but others values are fixed. N is also fixed, n is sample size, which is a single number. So what is the difference between these two? The difference is in this, sorry, this is x bar, this is x bar. The difference is in the second case, we use S instead of sigma. So what is the formula of S? S is, we know that S is equal sigma of xi minus x bar square divided by n minus 1, right? The square root of this. So we know this. So you can see that S is in terms of the values of x, right? So that's mean x bar is also in term of x, S is also in term of x, and x is random. So how many randomness we have here? We have two random things, right? X bar, which is x, which is the function of x, that's mean which can be written as in terms of x, and S is also can be written in terms of x. And x is random, so that's why S is random and x bar is also random. So that's mean we have two randomness here in the numerator and in the denominator. But in this case, we had only one random value, x bar, but the others values are fixed, right? Mu is fixed, sigma is fixed, n is fixed. They are not in terms of x. So that's why this is normal distribution, but this is not a normal distribution. This is something else. It follows some other distribution. That distribution is called T distribution or student T distribution. It is named as student T distribution because the guy who published this distribution in a journal, so actually he couldn't publish it on his name. So that's why he has to use this name, like he used this name, student T distribution, instead of his name. Okay, so the properties are very similar. So you can see here, you will not find a very big difference between these two distributions, but there is. So we have the standard normal curve and T curve. So the standard normal curve, the green one is the standard normal curve, and the T curve is the blue one when degrees of freedom is 1. And what is degrees of freedom? Degrees of freedom is sample size, in this case, sample size minus 1. So DF is n minus 1. This is called the degrees of freedom. So that's how many variables we have which are independent or which are free. So that's why it is called degrees of freedom. Okay, so you just need to remember that in this case, in T distribution, the degrees of freedom is n minus 1. That's it. Okay, so when degrees of freedom 1, this line is the distribution. When degrees of freedom is 6, then this is the distribution. But when we have a standard normal curve, the green one is the standard normal curve. So now you can see the difference between T and the standard normal curve. So if you look at the tail, you can see here it's more spreaded, right? It has thick tail. The T distribution has thicker tail compared to the standard normal distribution, right? So you can see here. So if you consider degrees of freedom, so less degrees of freedom, it will be like this. And so that's mean the tail has a very thick tail, the T distribution. That's the difference. Okay, so when the sample standard deviation is not known, when sigma is unknown, we do not know the values of sigma, we use S. In that case, we have to use T interval to construct the confidence interval for mean. So that's when we have to use this one, X bar minus. This is called the T score, or the value of T. Okay, so it has some very good properties. The basic properties of T curves, property 1, the total area under the T curve equals 1 because it is a density curve. So we know that for the density curve, the total area under the curve is 1. Property 2 is a T curve extend indefinitely in both directions. So you can see that it extended indefinitely in both directions. And property 3 is a T curve is symmetric about 0. So you can see here, this is symmetric about 0, and Z curve is also symmetric about 0. So they have the same property. Number 3, property 4, as the number of degrees of freedom become larger, T curves look like increasingly like the standard normal curve. You can see here, when it is 1, it has very thick tail. When we increase to 6, is very close to the standard normal distribution. So if you keep increasing the degrees of freedom, that's mean the sample size, then it will become actually close to a standard normal distribution. So it will become approximately a standard normal distribution. So that's why when we have large sample size, even we do not know the value of sigma, we know S, still we can use Z interval if we have very large sample size, because it will become approximately normal distribution. And you can see here, when we increase the degrees of freedom, that's mean the sample size the t curve become very close to the standard normal curve. Okay, so to find the value of t, we can use t table. So it is similar to the z table, but only difference is in z table we didn't need any degrees of freedom. We had only the z score and the probability. But from the t table, if you want to find the t value or if you want to find the probability, you need two things here. You need t score to find the probability and the degrees of freedom. So one mean t interval procedure. So how do you construct a one mean t interval? So the purpose is same. We will construct the confidence interval for the population mean. And for z interval, we did the same thing. We constructed the confidence interval for mu. So we had some assumptions for z interval, and for t interval, we will also have some assumptions as well. So the first one is simple random sample. This is the same assumption. We also had this assumption for z interval. And number two is normal population or large sample, and sigma is unknown. So only difference is sigma is unknown. So in previous case, we had sigma is known. Now we have sigma is unknown. So step one is for a confidence level of 1 minus alpha, use table 4 to find t alpha over 2 with degrees of freedom n minus 1, where n is the sample size. So if the confidence level is 1 minus alpha, we need to find t alpha over 2, the critical value. So from this table. So we have t alpha over 2 and the degrees of freedom. So you need also degrees of freedom, df n minus 1. So second step is find the confidence interval for mu, and the confidence interval will be in this form. So x bar plus minus t alpha over 2 times s over square root of n. And in previous case, it was x bar plus minus z alpha over 2 sigma over square root of n. So it's similar, but the only difference is we have s here, but we had sigma in previous case. We calculated z alpha over 2. Now we have t alpha over 2. So last step is interpret the confidence interval. Okay, so we have a data set, and this is the normal score. Actually, we use the normal score to see whether these data follow normal distribution or not. So, and we already discussed this in this class. So normal probability plus for chicken assumption. So this is the original data. We had one outliers here, and this is the normal plot. But when we remove the outlier, we do not see any change here, right? This one and this one, not that much different. So that's mean if we remove the outliers, they are similar. So the outlier is not affecting. Okay, so now we'll find a confidence. We'll go over some example for t interval. So find a confidence interval for a mean of a population when use the one mean t interval. So we'll use one mean t interval procedure with the sample mean, sample size, and sample standard deviation. Okay, so in part A, the confidence level is given below. So what is the confidence level? This is 98%. So part A, we have confidence level which is 98%. So alpha is 0.02, right? Alpha is 1 minus 0.98. So that will be 1 minus 0.02. Okay. So now we have to construct the confidence interval. So we know the value of S. So what is the value of S here? This is 2. We know n equals to 36, and x 36 is large, so that's fine. So this satisfies the assumption. So x bar is 17. X bar plus minus t alpha over 2 times s over square root of n. So we have x bar, we have s, we have n. So the only thing we have to find t alpha over 2. So alpha over 2 is 0.01. So if you divide so it's not 0.01. If you divide 0.02, so this is 0.01. So alpha over 2 is 0.01. Now we need to find T alpha over 2. So how can we find this? We have to look at the T interval, right? We have to find T alpha over 2. So to find the T alpha over 2, you need alpha over 2 and the degrees of freedom. So what is the degrees of freedom in this case? DF, which is n minus 1. N is the sample size, which is 36 minus 1. So that's mean the degrees of freedom is 35. So you need these two numbers to find the critical value for T interval from the T table, okay? So here we have, I'm sharing a T table with you. Okay, so give me a second. Okay, so let me share this one with you. Okay, so what was the value of alpha over 2? Alpha over 2 is 0.01. So where is 0.01? So this is 0.01. So we have 0.01 here. Yeah, for confidence interval, we'll consider truths, but you can also use different T table. So it's better to use the T table from the textbook. And what was the degrees of freedom in our case? 35, right? So we have the degrees of freedom for 30. We do not have 35 in the table, but it's fine. So for 30, this is 2.75. And for 60, this is 2.66. So that's mean in between the degrees of freedom in between 30 and 30 and 60, there is not that much different. It's 2.75, and for 60 it is 2.66. So that's mean you can consider 2.75. That will not hurt the confidence interval that much. Or if you have the exact value for degrees of freedom 35 in the table, that will be perfect. Or if you do not have, then you can consider the closest one. So 35 is close to 30. So that's mean we can use 2.75. So the T score is 2.75 in this case. So T alpha over 2 is 2.75. So we have X bar, which is 17 plus minus 2.75 times S over a square root of n, 2 over a square root of 36. So if you simplify this one, then it will be 2.75 times 2 divided by 6. So it will be then 17 plus minus 0.917. So this is the confidence interval. So if you subtract 0.917 from 17, you will get the lower limit of the confidence interval. And if you add 0.917 with 17, you will get the upper limit of the confidence interval. So this is the confidence interval we have. Okay. So the next part is obtain the margin of error. So this part is the margin of error. So we already have the margin of error, right? The part B, the margin of error is 0.917. So we already calculated this one. So part C is obtain the margin of error by using the formula T alpha over 2. Okay, so obtain the margin of error from the confidence interval. Yeah, you will actually get the, okay, so confidence interval of the population mean and T alpha over 2 S over, actually you will get the same value. So in part B and C, because in confidence interval, we also use this one, right? T alpha over 2 times S over square root of N. So you'll have the, actually you will have the same value. Yeah, in part C, it will be also 0.917. Do you have any question? Actually, it is very important to understand this chapter clearly. Otherwise, if you have any confusion, you will not be able to follow the following chapters. So if you have any questions, if you have any confusion, please let me know. Because in the following chapters, we'll be learning hypothesis testing for one population mean and hypothesis testing for two population mean and confidence interval for two population mean. So if you have any question, please let me know. We'll discuss it again. And if you have any confusion, then you will not be able to follow the following chapters. Okay, so here we have one more example. And we have the data set, we have the sample mean, and we have sample standard deviation. So since we have S, we do not have sigma, so we'll use actually T interval, right? Because we have S, so that's mean it will be X bar plus minus T alpha over 2 times S over S square root of N. So X bar is 18.36, S is 7.33, and N is the sample size, and which is, I think this is 20, right? Yeah, sample size N is equal to 20. And T alpha over 2. So you have to find the T alpha over 2 for 99% confidence interval. So alpha is 0.01. So alpha over 2 will be then 0.005. You have to find T alpha over 2. So then the confidence interval will be then 13.67 to 23.05. This is the lower limit and this is the upper limit of the confidence interval. So what is the degrees of freedom here? Good question. Yeah, what is the degrees of freedom here? Anyone? So what is the degrees of freedom in this case? So degrees of freedom is N minus 1, right? So here N is 20. So degrees of freedom will be 20 minus 1. So that's mean it will be then 20 minus 1. So that's mean 19. So in this case, the degrees of freedom is 19. Okay, so we are done with, we finished chapter 8. So, and we have 3 more chapters, I think. Chapter 9, chapter 10, and chapter 11. So do you have any question from chapter 8? Okay, thank you. Okay, then we'll start chapter 9. This is also about one population mean, but we'll do hypothesis testing for one population mean. So how many of you heard about hypothesis testing? Do you have any idea about hypothesis testing? So what do we do in hypothesis testing? So actually we'll have some hypothesis. That's mean we'll have some assumption. And we'll have a statement. The hypothesis is an statement. And in hypothesis testing, we'll have 2 statements. One is called the null hypothesis, and the other one is called the alternative hypothesis. the null hypothesis will consider that one is true. And we'll test the alternative based on our data. So first we'll discuss about the terms of hypothesis testing. So what is null hypothesis? What is alternative hypothesis? And what is the hypothesis test? So null hypothesis is a statement, a hypothesis which is to be tested. And we use the symbol H naught to represent the null hypothesis. Okay, for example, if someone make a statement that the average score in the first exam of our class is 80. Someone claimed that. Now we want to test based on the data. So we'll collect the data. That's when we'll ask the student about their exam on score, and we'll calculate the average. And based on the data, we'll test the claim, whether this claim is true or not. So we'll test that. For example, if a company, like consider a company who makes cereal or something else, or maybe who makes batteries, and they claim that the battery's lifetime is 6 months. They produce specific batteries, and they claim the battery's lifetime is at least 6 months. So that's been more than 6 months. Okay, so now we'll test whether their claim is true or not. So what do? We collect data, and based on the data, we'll do a statistical test, and then we'll determine whether their claim is true or false. So that is called hypothesis testing. So in that case, their claim was the battery's average lifetime is at least 6 months. Okay, so null hypothesis is the hypothesis to be tested. So that's when their claim. They claim the average lifetime is 6 months. We use the symbol and we use H naught. This is called H0 or H naught. And we use this notation to represent null hypothesis. And alternative hypothesis is considered as an alternative to the null. So it's the opposite of the null. So let's consider the previous example. The company claimed that the average lifetime of the batteries is more than or is 6 months. So what is the opposite of this? The average lifetime of the batteries is less than 6 months, right? They say at least 6 months. So the opposite of that one is the average lifetime of the batteries is less than 6 months, right? So that is alternative hypothesis, and it is denoted by HA, A subscript A, or you can say HA. So now we'll perform a statistical test to check whether their claim is true or false. This test is called hypothesis test, and it will be based on the data. Actually, we'll determine or we'll decide whether null hypothesis should be rejected or in favor of the alternatives, or cannot be rejected. Okay, so when we perform a statistical test, a statistical hypothesis test, there might have some error. We might, because we are performing a test, so we might do some mistake. So there is a chance that we might do some mistake, and this error is called type 1 error and type 2 error. So in hypothesis, we have H0 and HA. So we'll perform a test. This is null, this is alternative. So based on the test, we'll make a decision, and our decision will be either we reject H0 or fail to reject the null. So we have only these two decisions based on the statistical hypothesis test. Either we'll reject the hypothesis, sorry, null hypothesis, or we'll fail to reject the null hypothesis based on our test results. So, and when we make decision, we might make error. And there are two types of errors, type 1 error and type 2 error. So what is type 1 error? Type 1 error is rejecting the null hypothesis when it is in fact true. So based on our data, because we are collecting a sample, and this sample might give us, this sample might lead us to make wrong decision. So if we reject the null when it is in fact true, that's when we made a type 1 error. And if we fail to reject the null when it is in fact false, so sometimes it might happen that we fail to reject the null when in fact it is false. This is called type 2 error. So that's mean we can make type 1 error and type 2 error. So we also need one more thing, significance level, the probability of making type 1 error. So this is the probability of making type 1 error. So this is probability of making type 1 error. And in confidence interval, we know about, from the confidence interval, we know about alpha. Alpha is the significance level. So this is 1 minus the confidence level. And this is the probability of type 1 error. So that's mean how much error we'll tolerate. That will be determined by the value of alpha. Okay, so relation between type 1 error and type 2 error probabilities. For a fixed sample size, if the sample size is fixed, the smaller we specify the significance level alpha, the larger will be the probability beta. So that's mean if alpha is smaller, beta will be large. Beta is the probability of type 2 error. So alpha is probability of type 1 and beta is the probability of type 2. So if alpha is smaller for a fixed sample size, beta will be larger. If alpha is large, beta will be small. Okay, so possible conclusions for a hypothesis test. Suppose that a hypothesis test is conducted at a small significance level. So that's mean alpha is very small. If the null hypothesis is rejected, then we conclude that, so null hypothesis rejected, then we conclude that the data provides sufficient evidence to support the alternative. Okay, so when we make our decision, actually we can make two decisions. One is we reject the null in favor of alternative. That's mean when you reject the null, that's mean our decision is favoring the alternative. And the other decision is if the null hypothesis is not rejected, that's when we fail to reject null. That's mean the data do not provide sufficient evidence to support the alternative. So one decision is we reject the null. That's mean our data is providing sufficient evidence to support alternative. And the second decision is the null hypothesis is not rejected. That's when we fail to reject null. That's when their data do not provide sufficient evidence to favor the alternatives. Actually, that's how we interpret the results of the hypothesis test. Okay. So now we'll go over some example. Suppose that in hypothesis test, the null hypothesis is in fact true. Now the question is it possible to make a type 1 error? So we need to explain our answer. Okay, so let me explain the type 1 error and type 2 error one more time. Then we'll go over this example. Okay, alpha is probability of type 1. So hypothesis, when we do hypothesis test, the first thing is we have to write the hypothesis. We have null, we have alternative. And decision is either we reject null or fail to reject null. Okay, so now alpha is we reject null when in fact null is true. So this is the type 1 error. And type 2 error is we fail to reject null when in fact null is false. So now our first problem is, suppose that in hypothesis test the null hypothesis is in fact true. So null hypothesis is true. So is it possible to make a type 1 error? So what do you think? Can we make a type 1 error in this case? So when our null hypothesis is in fact true. So null is true, but our decision could be we reject null or fail to reject null. So what will happen if we reject null? Okay, so okay. So let me make this chart. So our decision. Our decision could be either reject null or fail to reject null. FTR means fail to reject null. So that could be our decision. So now consider null is true. Or null could be false, right? This is the true scenario. The true fact is null could be true or null could be false, right? Okay, so when null is true, so if we reject null, when null is true, this is called the type 1 error. This is type 1. Okay, so when null is true and we fail to reject null, so that's mean our decision and the true case, they are same, right? So that's mean this is correct decision, right? We didn't do any mistake. This is correct. And what will happen here? The decision is reject null when null is false. That's mean this is true. Null is false and we are rejecting null. We are not supporting null. So that's mean this is also correct decision. And what will happen here? Our decision is fail to reject null when null is false. So when null is false, we are supposed to reject null, but we fail to reject null. So that's mean this is mistake. This is error. So this error is called type 2 error. Okay, so when we make type 1 error, when the true fact is null is true, right? When null is false, there is no chance that we'll make a type 1 error, right? Because our decision will be the reject null or fail to reject null. When null is in the true fact is, but our true case is null is false, in that case, we do not have any chance to make type 1 error. And if the true scenario or true case is null is true, and based on our decision, we can make either correct decision or we can make type 1 error. So now the question is, suppose that in a hypothesis test, the null hypothesis is in fact true. That means the true scenario is this one, right? Null is true. So is it possible to make a type 1 error? So what do you think? Is it possible we can make a type 1 error in this case? Anyone? Okay. So how about others? So I got just one response. You said no. Okay, so when we can make type 1 error? If the true scenario is null is true, And in this case, it is given that the null hypothesis is in fact true, right? The true scenario or true case is null is true. So that's mean there is possibility that we can make either correct decision or we can make it a type 1 error. So that's mean it is possible that we can make a type 1 error, right? Is it clear? Okay, it's already 12:21. Yeah, I will finish in a minute. So yeah, it is possible, right? Yeah, that's correct. Thank you. And part B, is it possible to make a type 2 error? No, it is not possible, because when we make type 2 error, when the true case is null is false, in that case, either we'll make correct decision or we'll make it a type 2 error. Okay, so we'll discuss more about the hypothesis test, the type 1 error, type 2 error in the next class. And you will have quiz in the next class. And the last 30 minutes of the class will be the quiz. And it will cover chapter 7 and chapter 8. Okay, thank you. See you on Thursday.